Okay. All right, sort of continuing on from where we were, talking about groundwater movement from a conceptual standpoint, not a quantitative mathematical standpoint yet. So we talked about how fast groundwater moves. It can move really slow, centimeter per year in shales, or it can move pretty fast, 100 meters or so a day in loose sand. Typically centimeter to meters per day for most rock types. The velocity of groundwater movement depends on a couple of variables. One of the main controls is the permeability. If it's highly permeable, it can move faster. So when your permeability is high, your velocity is also high. The other thing is that it needs a reason to move. It has to move in response to something. And that could be, as we said, the beginning or last part of class, it could be the slope of the water table, how much influence gravity has on it. And later we're going to talk about movement of water within an aquifer, where the water is moving in response to pressure. So the magnitude of the pressure gradient can also affect it. And when I talk about a pressure gradient, I'm talking about how much the pressure changes over some distance. So if I, let's say, had an area in my aquifer where there was lots of pressure, big P, and then really close to it, there was small pressure. That is going to result in a very large, fast-moving water. Your change in P is big, your distance is short, that means your pressure gradient is high. If you had a case where you had a moderate amount of pressure, and somewhere fairly distant you had a little less pressure. In this case, your movement isn't going to be nearly as fast. The change in P is much less, your distance is much greater, so the speed of the movement is going to be a lot less. We'll come back to that latter topic a little later in the semester. Okay, so let's look at a couple of scenarios here. Let's say here's your surface. What's your water table going to look like? It mimics the surface, right? So it might do something like this. It'd be really steep down going here. Something like that. So in response to gravity, where's the water going to move the fastest? Yeah, where it's steepest, right? So you're going to have the maximum velocity here. You have a little bit of movement that direction, a little bit of movement that direction, maybe a little bit of movement that direction, a little bit of movement that direction. What about, let me get the right color, about right there.
Since you have a really high amount of pressure on that left and outside, there's nothing causing like an equilibrium. You're probably still going to see movement this way.
Yeah, actually you're right. Over time, you're probably going to have a general movement of water in that direction. But this place right here, at least at this point in time, it doesn't have a slope, right? So you're probably not going to get much water movement there. You'll get water movement from the higher spots of the water table down. Probably not a lot of movement right there. But in general, you're going to have, and we're going to talk about terminology later in the semester, but you're going to generally have a movement of water from left to right because this is where your highest pressure is going to be because the water table is up the highest. We'll get to those concepts later. So over time, your water's probably going to move generally from left to right, but locally you might have little movements that more mimic the blue arrows. As I said, last part of class, if you have your tree there, your water table mimics the surface. If the slope here equals 0, the slope of your water table is probably going to equal 0. In this case, your movement isn't likely. Unless there's some sort of pressure in there that we haven't accounted for yet. All right, I do this in my environmental geology class. So some of you have seen this, but others haven't. So let's say I had this situation right here. There's a land surface. Here's my house. Here's your house. What does the water table look like? Mimics the Earth's surface. How's water going to flow in this diagram?
From left to right.
Generally from left to right. Pretty fast where it's steep. Okay? So let me use orange. So here are the boundaries of my land, and then this is the boundary for your land. So here's our lot line right here. Divide your land from my land. Okay, I live out in the country and you live out in the country. I need to have some way of removing wastewater from my house. When I flush, when I run the dishwasher, when things go down the drain, that water's got to go somewhere. Okay? But I live out in the country, so there's no sewer pipes that are going to take it to town, take it to a wastewater treatment plant. What do we use in rural areas for wastewater disposal? Something called a septic tank. All right. Where's my septic tank likely to be if I'm smart?
Lower elevation than your pipes.
Okay, and okay, so lower elevation. So I've got this flat area and then it starts to go down here, right? One thing about septic tanks is that they leak sometimes, and they can leak nasty water that came out of your house into the ground. You don't want that water flowing back towards your house, and I'm likely to have a well here too, okay? So where am I going to put my septic tank and where am I going to put my well? Those are two things I need if I live in the country.
Your well would go closer to your house.
Okay, so I could put the well, say, right here, right? I need my well to penetrate into the saturated zone, so I get a flowing well. Where am I putting my septic tank?
Away from your house.
All right.
Underneath, like, as far deep as you can go. So it goes underneath the water table.
Why do you want it in the water table?
You want it past the water table,
The well or the septic?
the septic tank.
How come?
Because if it leaks, the water will only go down. It's not like if you put it at the water table, your septic fluids are going to spill out, and that's going to be nasty. Or you could put it deeper down, and it can't move back up.
It can still leak, as it turns out. Either way, even you can get usually they're put in the unsaturated zone. Sometimes these things are made of metal. Mostly they're made of plastic these days. But a lot of times we're going to put them in the unsaturated zone, because the thing that you actually want with a septic tank is you want microbes to break down some of that material, and they exist best in the unsaturated zone where there's air. So let's put it in the unsaturated zone. So I've got some options here. You said I should put it maybe down this way, right? What was your reasoning?
You're getting clean water in your well before.
You don't want this to impact this, right? So if this leaks, if your septic tank leaks, where's the water go?
Down the hill.
It's going to go down the hill. Sadly, it's going to go to your house. Hopefully, the nasty stuff will break down by the time it gets there. Hopefully. Now, if I'm an idiot and dump gasoline in my septic tank or some other substance that isn't going to break down, then that travels downhill and upsets the neighbors, and it's not good. So yeah, we want to place things with a knowledge of how water is going to move in the subsurface. Yes, we don't want it moving towards our house. Sadly, we don't care as much about our neighbors. But that's something when you do buy a house in a rural area, you need to look at what's uphill from you. Try to figure out where their septic is. Make sure it's not going to impact your land, because these things actually happen a fair bit. Okay. Let's move on. Marching through some terms. I've used this term a few times today, aquifer. An aquifer has different definitions according to which books or papers you're reading, but I think the simplest, easiest, most workable definition is that an aquifer is a body of rock and or soil that easily transmits groundwater. Now this term right here, easily, kind of a wishy-washy term. And that's kind of for a reason. Because you don't have much control about the rocks that are beneath your house. Okay? You buy a house, the rocks beneath your house are the rocks beneath your house. If you live up on the Pine Ridge Reservation in South Dakota, guess what kind of rocks you have beneath your house? you have about 20 different kinds of shale. That's all you have. Shale unit after shale unit after shale unit. Each shale unit's a little different, but they're all shales. What's your aquifer going to be? The best of those shales. Now, you might live in another area, though, that has porous limestone, porous sandstone, porous limestone, porous sandstone, shale, sandstone. That shale might actually be more permeable than the best one beneath somebody on Pine Ridge. But in your area, you're not going to use it because you have those nice sandstones and limestones beneath that are going to transmit water faster, easier, and have better water quality. So I guess the best way to say this is that one person's aquifer may be another person's aquiclude, which is the opposite of aquifer. You may also come across the term aquitard, synonymous. In other words, one person might be using a really poorly permeable shale as an aquifer because that's just the best rock unit they have. In another area, you'd never touch it because you have so many better options. So that's why we use aquifer as kind of a relative term. In general, we're going to start out for a good aquifer, you want something that's porous, permeable, and gives you good water quality. Good aquifers generally are sandstones. Limestones. Limestones tend to be good aquifers, but they also tend to have what's called hard water. Hard water is water that has lots of minerals dissolved in it. Limestone is made primarily of the mineral calcite. If you guys remember back to physical geology, maybe mineralogy, you know that's calcium carbonate. So when limestone dissolves in water, you get lots of calcium, you get lots of bicarbonate, lots of stuff dissolved in your water. So it tends to be hard water. Nothing wrong with hard water. It's actually good for you. It has lots of dissolved minerals in it. It's hard on pipes, though, because it scales pipes. If you've ever seen like the white, crusty deposits that can be on pipes, that can be the calcium carbonate coming back out of solution. So it can be hard on pipes. Dish soap. Soap in your shower doesn't lather as well when you have hard water. That's why a lot of people soften their water, is get the soap deposits out. But generally, it's still really decent water. Alluvium is another good aquifer. You guys know what alluvium is?
Basically, like the remnants of erosion.
Yeah, and it tends to be found in river valleys. That's the best place to find good deposits of alluvium. So let's say, I'm going to try to draw this. This might be a disaster, but we're going to give it a shot. So let's say we have sort of a big U-shaped valley. Okay? Sides of that valley are going to erode over time. That stuff's going to roll down to the bottom and accumulate at the bottom of the hill. Okay? So you're going to have a deposit of what's called alluvium down here in the bottom. And it's just going to be rocks of various sizes, poorly sorted if you had your physical geology class, lots of different sizes, big rocks, little rocks, all sorts of rocks in between that just accumulate down here at the bottom. Tends to be pretty porous. Now if you have a river flowing in here, that water can sometimes move out of the stream into the alluvium and give you a nice little groundwater deposit in that alluvium. So if you drive up like Poudre Canyon and see the cabins that are along the river, what they're doing is, it's going to get small and messy, but if they have a little house right here, they're going to sink a well down and pull groundwater out of that alluvium. What's the origin of the water that they're ultimately pulling out? It's the river, right? It's just river water that's seeping into the alluvium. But as it moves through the alluvium and all those pore spaces, most of the impurities are going to get filtered out on the surfaces of those rocks, which have little positive and negative charges on it. So it acts as a nice filtering system. But if you put your well 2 feet from the river, there's not a lot of distance for the water to filter out. And if there's any pollutants in the stream, you might very well get pollutants in your groundwater. You may have to treat it. You may have to dump some chlorine in it, some bleach. But this is a source of water for a lot of people. It's a lot better than just pulling it out of the river and drinking it, because if you're doing that, you're probably drinking cow crap and Lord knows what's coming down from higher elevations. So that movement through that alluvium does help to filter out a lot of the impurities. Other good aquifers are fractured igneous and metamorphic rock. Typically, these two rock types have really low porosity and really terrible permeability. But if you're in a mountain building area where it's all broken up, there can be some really nice pathways for water to flow. So my wife has a house outside of Steamboat Springs. There are about 20 houses in the area. It's on a hillside coming down from a big mountain out of town. So we have a septic tank, and because drilling wells is so expensive, we have a community well. All 20 residents share the well. Where's the well relative to the houses if we're smart? What's that? Yep, it's uphill from my house. We have the second highest house on the hillside. There's one other house above us. So we only have to worry about one other septic tank. And that guy lives pretty much far enough away that we don't worry about it. And then the well's located up higher. So everybody's septic tanks drain downhill and they don't affect the well water at all. So that's good. The area is all igneous rock. Solid. I mean, if you took a piece of this rock and looked at it, there's not a pore in it. It's just solid, dense, heavy rock. But because it's in the mountains, there's big fracture zones from mountain building, and our well is actually placed right into one of these fractures. So it gets lots of water moving through. It's replenished every year by snowmelt. So that's where we get the water. They have to dump a little chlorine into it every spring, get out the impurities. We have lots of elk and cattle in the area. They crap on the ground. That stuff filters down. It's possible to get some of it in our water. So we throw in some treatment to get rid of it. But that's our water. Pretty clean, very lightly treated relative to city water. It's good stuff. But it comes out of one of these because that's the only rock we have in the area. There's no sedimentary rocks in the area at all. It's kind of the core of the Rockies. So we just find a fracture where water can flow through. All right, any questions so far? Okay, so two final terms in this section. One is called a perched aquifer. And the second, we talked about a little already, is called a spring. So let me draw so there's a ground surface. Generally, the water table mimics the topography that lies above it, but there can be variations depending on, we'll get into it a little later in the semester, but it is possible to have this sort of situation right here, where you got your water table. It follows the Earth's surface generally, but right here it intersects the Earth's surface. And what happens here is that water pours onto the ground. So this is the water table, where water table intersects the Earth's surface. It's called a spring. If the water table goes up, the location of your spring may be higher up the hill. If your water table drops, the location of your spring might be a little farther down the hill, or the spring might dry up altogether. In a lot of places, springs are seasonal. You find them in the spring when the water table rises up high enough to intersect the Earth's surface. But then once the snowmelt contribution goes away, water table lowers, and the springs may dry up for the rest of the year. Now, in some parts of the Great Plains of the U.S., there are places where we get little clay or shale lenses. These are just little irregularities in the subsurface rock, where you might just have a deposit of impermeable clay or shale. And what can happen is water can actually sort of pool, it's going to be a bad drawing here, can pool on top of this. It percolates down from above, but it can't move through this clay layer right here. And it just sort of accumulates on top of it. This is what is called a perched aquifer. It's a localized, saturated zone that lies above the main water table. Now, the reason I bring it up is that little factoid I gave you a little earlier in class, that it was $20 to $30 a foot to drill a well. Well, here you might have to drill down this far to get enough water. Or if you hit it just right, you might be able just to drill into this perched aquifer, which is a little bit above. A lot of times these are big enough to hold enough water for households. So in some areas, if you're lucky enough to have one of these, and if you're lucky enough that your driller finds it by accident, because they're almost always found by accident, because there's really no way to see this in the subsurface, you can save a lot of money. You have to be careful that you don't over pump these because they obviously don't hold the volume of water that the main water table holds, but it can be a cheaper, steady source of water for small households in rural areas. So these are talked about a fair bit in the central part of the US. They're pretty common. All right, any questions? All right, we're going to start a new chapter. Probably only go 10 more minutes, and then I'll quiz up the people who need to be quizzed. Okay? So we're going to start looking at how water moves on Earth. Not just in the ground, but how it actually gets there. How water gets into the ground is pretty important, because as it makes its path from its origin to its residing place underground, it can come in contact with a lot of human activities that can pollute it, damage it, leave it unusable by humans. So we're going to start off with a concept that you've probably seen somewhere in the past. We call it the water cycle or the hydrologic cycle. And we're going to start with water in our atmosphere. And we're going to trace water from the atmosphere to various locations on the Earth, and from the Earth up into the atmosphere. We're going to look at all the different potential pathways where a water molecule could go. So if you have a drop of water up in the atmosphere, water vapor, humidity, that water condenses into a raindrop. Gravity can pull it downward. Where can water in the atmosphere end up on the Earth's surface? It's a couple different places. Just to kind of get you started, it can end up on the land surface. Rain falling on the land. That's called precipitation. I'm just going to put a P there. So when it rains, that water can land on land. Where else could it land? Where's it likely to land? Most likely, percentage-wise. The oceans, okay? Most of the Earth's surface is covered by oceans. It's most likely to land in the ocean. Rain onto the ocean is also precipitation. This might be a little more cryptic, so I'm not going to ask, but if it doesn't land on land and it doesn't land in the oceans, the one other place that it can land is on water bodies on land. So lakes, rivers, and glaciers. And that's precipitation. Okay, now with this start of a cycle, let's think about land. It's what you have the most familiarity with. A raindrop lands on the land surface. What can it do? What are its options?
anywhere but up.
Can it go up?
Unless it evaporates.
It can evaporate, so it can go back in the up into the atmosphere, right? E for evaporation. What else can happen to that raindrop? It can absorb into the ground. So if you think about our diagram of the subsurface with water, we had a couple zones, right? What zone does it enter first? Okay, so it goes into the unsaturated zone. I'm just going to write vadose zone so that you get used to the term and it's shorter, fits in the box better. That process of moving down is called infiltration. Gravity could keep pulling it down, eventually bringing it down into the saturated zone. That movement through the vadose zone to the saturated zone is a process called gravity drainage. Anything else happen to the water that lands on the surface? It can evaporate. It can go into the ground.
Another body of water over.
Perfect. You must have read my notes. So it moves into lakes, streams, or rivers through a process called overland flow. Now, if you take one of Dr. B's classes, her hydrology class, that's what you're looking at. You're looking at stream flow. Spend a whole semester just dealing with that. And there's a boatload of jobs out in the real world to look at overland flow, basic hydrology. Okay? What else could happen to that water? Okay, so we got water soaking in the ground, water evaporating, water running off. There's one more place water can end up. And you guys don't think about it ever because you're geologists. By? What would suck water up out of the vadose zone?
Plants.
A plant. So plants can uptake. This gets a little messy. I'm going to put a layer of plants on here, green. So it could be absorbed by plants, and that is not a minor amount of water. It can be significant, especially if you're in a rainforest. We're talking a lot of water. What do plants do? What are their primary processes? During the day, they sit out in that warm glow of the sunlight and they do what? They photosynthesize, which means they take sunlight, they suck in carbon dioxide. Through photosynthesis, they extract the carbon, they build their cells, right? And they give off oxygen. What happens at night? It happens during the day too, but it happens at night. Through a process called respiration. And they can give off something called water through a process called transpiration. Okay, so plants can transpire. You can do this like early morning. You can put I don't know, some clear plastic over the grass, and the dew will just sort of accumulate beneath that, right? That's plants giving off some water as well as some evaporation from the soil. As it turns out, it's really difficult to separate the evaporation off of the land from the transpiration going on with plants. So what we tend to do is just lump them together through a process called ET, or evapotranspiration. Transpiration. So it's evaporation and transpiration, but in practice they're almost impossible to separate, because you always have plants on the ground to some degree, unless it's just bare soil, which isn't that common. So to separate out the two relative components is difficult, so we just lump them together. Call it ET. And it's a big component in this process. We'll talk about it a bit. Okay, so water in the vadose zone. It can move down by gravity. We have this gravity drainage. It can also move sideways. It'll move sort of downhill. And even though it doesn't look like downhill because of my diagram, it can make its way into lakes, streams, and rivers. I'm going to draw on this and I'm going to erase it, but let's say we have a river valley. Let's say this is our water table. So we can have some water from the saturated zone moving into rivers. Okay? Do you notice the streams flow even when it's not raining? Look at the Poudre River in the summer. It might not rain for months, but there's always water flowing, right? If you go up to the highest regions, the snow's all melted. So where's the water coming from? Well, as it turns out, it's coming from the saturated zone. This is a process called base flow. So here we can also get water from the saturated zone moving into streams, lakes, and rivers through a process called base flow. Up here is the unsaturated zone. That water can also move into lakes, streams, and rivers very slow. And that's a process, we're not going to spend much time in this class on it because it's really small. It's something called interflow. So you can move water from the land surface as runoff into lakes, streams, and rivers. You can move a teeny tiny amount of water from the unsaturated zone into lakes, streams, and rivers. It's a process called interflow. It's probably the last time I'll mention it in class. Just about all hydrologic applications ignore it. And then you can have water moving from the saturated zone into lakes, streams, and rivers. And that's a sizable amount. We're going to spend all of next week talking about it. And that's called base flow. So we're going to talk a lot about base flow the next few weeks. Where do rivers ultimately flow to? Oceans. That's also called overland flow. You can get saturated flow into the ocean, also called base flow. Depending on where the sea surface is and where the water table is, you can actually have the ocean percolate water under the land in coastal areas. This diagram's getting wordy, but that's called subsea outflow. Really important in coastal regions. Where do most people on the planet live? Coastal regions. All right, I got to get rid of some of this stuff here. I need the space. Okay, just to sort of finish this up. So if you have ocean water, it can soak under a land surface. It can also soak into the seafloor. Ultimately, what happens to the seafloor on Earth if you give it millions and millions and millions of years? Subduction. So some of this water can be subducted. And where it ends up is the lower crust and mantle. Now, because of my background, I find this actually really cool. This water then, if this material gets melted, it can come back up to the Earth's surface as a volcano and become what we call juvenile water, new water, water released from rocks through volcanic outgassing. Just to kind of finish this off, we can get evaporation off of lakes and streams. We can also get evaporation off the ocean as well. So the big ones that we're going to talk about in here are overland flow. Not so much in here, a little bit in here, but a lot in other hydrology courses. We're going to talk a lot about base flow because it connects with the groundwater system. We're going to talk a lot about infiltration and gravity drainage. That's where our water comes from. We won't be able to spend too much time with subsea outflow. We won't spend too much time with precipitation and evaporation. That's for Dr. B's class. If you want to talk about volcanoes, you can take my volcanic geology class. And you pretty much have the water cycle covered. Okay, so next week we are going to talk, if I have my notes correct, we're going to talk about base flow, interactions between streams and groundwater. that's where we're going to go with this. Do you guys have any questions? Yes, sir.
It says outflow?
Subsea. Yeah, sorry about that. That is poor handwriting. Any other questions? Yes, sir.
How does like permafrost factor into groundwater?
It's a lot. Permafrost is permanently frozen soil mostly. Sometimes it can be so extensive that it's technically a saturated zone, where it's just a solid body of ice underneath. Sometimes it can be more like an unsaturated zone where you get frozen bits, but you still have openings that are available for air to get into. But it's kind of a big storage area. And it's not just water. There's gases that are trapped in there. That's one of the issues that climate modelers are dealing with right now, is a lot of permafrost is melting because of climate change, and trapped in the permafrost is lots of methane. And the methane then goes into the atmosphere, and that's one of these greenhouse gases that has a really high short-term effect. So it just exacerbates the climate problem even more. So it's a great question, because it's one of the areas in earth and climate science right now that's getting an awful lot of attention. The polar regions are changing drastically. Melting of permafrost is one of the drastic changes, and it's got kind of a chain effect. It's one of these feedback cycles in climate science. So yeah, it's a big area. And as you can imagine, when you have ground that's permanently frozen, water doesn't move very well. So it just sort of gets trapped there.
So it's kind of its own entity, separate from groundwater, kind of?
I mean, you can call it groundwater. It is water.
Yeah.
It's ground ice, you know. But that's water, and it's just not going to move by interflow or gravity drainage until it becomes movable, becomes a liquid. So it's a store. It's a water storage area. But with climate change, it's changing from permafrost to not perma. So it's becoming a system like we've sort of drawn out here. So yeah, so then you have to think, well, this area has been frozen for 30,000 years, and now suddenly the water can move. What sort of changes are you going to expect? Great question. Great area of science and research right now.